Ever stop to wonder how we can literally see inside the human body without making a single cut? Well, today, we're going to follow the incredible, super violent, and absolutely fascinating journey of a single electron as it creates the magic of an X-ray. It really all boils down to this one question, right? How in the world do you create a beam of energy that's powerful enough to pass through solid objects, but also precise enough to give us a picture? Well, the secret is to take one of the tiniest particles we know and turn it into a tiny, unstoppable missile. And this is where all the action happens. It's called an X-ray tube. And yeah, it looks pretty simple, doesn't it? You've got a negative end, a positive end, and a whole lot of nothing in between. But trust me, inside this simple-looking glass tube, we're about to unleash some seriously extreme physics.
Okay, so every story has a beginning. And for our electron, its mission starts at the source. Before it can go on this crazy journey, it has to be set free. This is the launch.
So, step one, we need a cloud of electrons ready to go. The way we do that is by running a current through this tiny little tungsten wire, heating it up to over 2,000 degrees Celsius. I mean, that is incredibly hot. And just like water boiling turns into steam, this intense heat literally boils electrons right off the surface of the wire. It's a process with a fancy name, thermionic emission. But here's the thing, these electrons are now free, but they're just kind of buzzing around all over the place. To get them under control, they're gathered into this little thing called a focusing cup. It's negatively charged, so its whole job is to push those electrons together, kind of herding them into a tight, focused beam that's aimed perfectly at its target.
All right, our electrons are launched and they're aimed. Now it's time for Act 2, a high-speed trip across a vacuum at speeds that are just, well, they're hard to even imagine.
To get that beam of electrons moving, we apply a massive electrical difference between the negative end and the positive end. And when I say massive, I mean it. We're talking up to 150,000 volts. This creates this incredibly powerful electric field that just grabs those electrons and slingshots them across the tube at more than half the speed of light.
So you might be wondering, why does this all have to happen in a vacuum? Well, think about it. At these insane speeds, hitting even a single molecule of air would be like running into a brick wall. The vacuum gives them a totally clear path, so the electrons don't smash into anything and lose all their energy before they even reach the target. It's all about having total control.
So our electrons are flying. Where are they headed? Well, every journey has a destination. And for these little guys, that destination is called the anode. And their arrival? It is anything but gentle. It is a sudden, violent crash.
And here it is. This is the target. It's basically a chunk of copper with a little tungsten plate stuck in it. As our stream of super-fast, negatively charged electrons slams into this positive target, bam! All of their kinetic energy gets converted in a violent flash. And in that one tiny instant, X-rays are born. But how, exactly, does that collision create X-rays? It's not just one thing that happens. It's actually two totally different interactions that are going on at the atomic level. And understanding both is really the key to the whole shebang.
Okay, so the first and by far the most common interaction is called Bremsstrahlung. It's a German word, a bit of a mouthful, that just means braking radiation. So picture our electron like a speeding car. As it zips past the heavy, positively charged nucleus of a tungsten atom, it gets pulled off course. It's forced to swerve. And in that swerve, it has to slam on the brakes, losing energy. That lost energy is instantly shot out as an X-ray.
And check this out, this shows it perfectly. You can see the electron's path literally bending as it gets near that nucleus. It doesn't actually hit it, it's a near miss. And the amount of energy it gives off just depends on how close it gets and how hard it has to brake.
So that was the near miss. But what about a direct hit? Well, that's the second type of interaction, and it's called characteristic radiation. This time, our incoming electron is like a cue ball in a game of pool. It comes in hot and smashes directly into an electron in one of the tungsten atom's inner shells and just knocks it clean out of orbit.
So that collision creates a hole, right? An unstable vacancy in the atom. Nature doesn't like that, so to fix things, an electron from a higher energy outer shell immediately drops down to fill that hole. As it falls down, it has to release a very specific, predictable amount of energy, an amount that is characteristic of a tungsten atom. And that little packet of energy? That's our second type of X-ray.
So here's the key takeaway. The final X-ray beam that actually comes out of the machine is a mix of both of these things. You get this broad, continuous range of energies from all that braking radiation. That's the smooth curve you see here. And then, sitting right on top of that, you get these sharp little spikes at very specific energy levels from that characteristic radiation.
But, and this is a big but, creating X-rays this way comes at a huge cost. This whole process is incredibly inefficient, which creates a massive engineering problem that absolutely had to be solved.
So I want you to think about all that energy we just talked about, all that power we used to accelerate those electrons. If all that energy slamming into the target, what percentage do you think actually becomes a useful X-ray? And the answer is kind of shocking. It's less than 1%.
That's right, over 99% of the energy is converted directly into heat. The target gets incredibly hot, instantly. A single exposure can make that little spot jump by 1,000 degrees Celsius. So the real challenge isn't making X-rays, it's stopping the machine from melting into a puddle on the floor.
So how do you solve that? Well, the first line of defense is just picking the right material. Why tungsten? It's perfect for two reasons. First, it has a high atomic number, 74, which just means it has lots of protons and electrons, making it way more efficient at actually producing X-rays. And second, it has a ridiculously high melting point, so it can take an unbelievable amount of heat before it even thinks about failing.
But you know, even tungsten has its limits. The very first X-ray tubes used what's called a stationary anode, where the electron beam just hit the same tiny spot over and over. That really limited how much power you could use. The brilliant solution was the rotating anode, a design that spreads that heat out.
So on the left, you see that simple, stationary design. But on the right, that's the modern marvel. Instead of a fixed target, the tungsten is shaped like a disc that's spun by an induction motor. And in a really clever bit of engineering, the motor coils are on the outside of the glass tube, while the rotor that they spin is on the inside the vacuum itself.
And this is the magic trick right here. By spinning that disk at up to 10,000 RPM, the tiny point where the electrons hit is constantly moving. So the intense heat, instead of being focused on one little spot, gets spread out over this huge circular track. It lets you use way more power and take lots of pictures back to back, which is essential for modern medicine. It's really the difference between holding a blowtorch on a single coin versus waving it over a spinning pizza pan.
So let's just think about that for a second. From boiling electrons off a tiny wire, to flinging them across a vacuum, to smashing them into a target that's spinning at 10,000 RPM just to handle the heat, that simple X-ray you get at the doctor's office is anything but simple. It really makes you wonder, doesn't it? What other technologies that we use every day are hiding this level of invisible, absolutely incredible engineering just to make them work?